We're going to find the area that's inside r equals 3 times the sine of theta and outside r equals 2 minus the sine of theta. What I'd like for you to do is pause the video and sketch the graph of these curves and then come back. I hope we have something that looks something like this. R equals 3 times the sine of theta is going to be a circle of diameter 3, symmetric with respect to the line theta equals pi over 2, and tangent to the pole. Outside the other curve, r equals 2 minus the sine of theta, is going to be a dimpled limicon with a maximum radius at 3 pi over 2 of 3 and a minimum radius at pi over 2 that's equal to 1. We want the area that is inside the circle but outside of the limicon. So we're looking at this portion that's the upper part of the circle, but we're going to have to cut out the portion that's inside the limicon. We need our limits of integration. Our limits of integration are going to be in terms of theta, and they're going to come from the points of intersection between these two curves. Now it looks like the curves intersect on the lines theta equals pi over 6 and theta equals 5 pi over 6, but we don't know how accurately I've drawn this. So we need to set 3 times the sine of theta equal to 2 minus the sine of theta to find the limits of integration. Finding out the theta values where these two curves equal each other will give us those limits. So it looks like we've got 4 times the sine of theta is equal to 2, or the sine of theta is equal to 1/2. And as the drawing indicates, we do have theta equals pi over 6 and 5 pi over 6 as our limits, but we don't take it for granted by looking at the graph, right? We have to do this actual work to solve for theta. As for our area, we are looking at the formula area equals 1/2 times the integral from a to b of, and because we have two curves, f of theta squared minus g of theta squared d theta. In this case, our f of theta is the blue circle, r equals 3 sine theta, and g of theta is equal to it's the green one, r equals 2 minus the sine of theta. I know that not because the blue circle is above the green curve in the first and second quadrants. I know that because if we draw a radial line from the pole out, then that covers our region, right, of which we're trying to find the area. The first curve that I encounter will be the smaller of the two curves. It has a smaller radius. The second curve that I encounter will be the larger of the two curves. It has the larger radius. So I'm thinking of r equals 3 sine of theta as f, and r equals 2 minus sine of theta as g. With that in mind, I'd like for you to go ahead and flesh out the integral and find the area. Squaring f, we get 9 times the sine squared of theta. Squaring g, we get 4 minus 4 sine of theta plus the sine squared of theta. And so our integral is 1/2 times the integral, actually, from pi over 6 to 5 pi over 6 of 9 sine squared of theta minus the quantity of 4 minus 4 sine of theta plus the sine squared of theta. Collecting some like terms, 9 sine squared of theta minus sine squared of theta gives us 8 sine squared of theta, and then we apply a power reducing formula and distribute the 1/2 in front of the whole thing. We end up with area is equal to the integral from pi over 6 to 5 pi over 6 of 2 minus 2 cosine of 2 theta, that's the power reducing formula and the 1/2 out front, plus 2 times the sine of theta minus 2, that's just from distributing the 1/2 into the other two terms. 2 subtracts out. We integrate the cosine and the sine. We end up with the area is equal to the quantity of negative sine of 2 theta minus 2 cosine theta evaluated from pi over 6 to 5 pi over 6. And by substituting those values into theta as appropriate, we end up with a final answer of 3 times the square root of 3.